all matter is made of atoms, which are indivisible. Dalton proposed that all matter is made of tiny indivisible particles called atoms, which he imagined to be solid, massy, hard movable particles. Second, all atoms of a given element are identical in mass and properties. Dalton proposed that every single atom of an element, such as iron, is the same as every other atom of that element. He also noted that the atoms of one element differ from the atoms of all other elements. A sodium atom is different from an iron atom. Elements may share some similar boiling points, melting points, and electronegativities, but no two elements have the same exact set of properties. Today, we still know this to be mostly true. In the third part of Dalton's atomic theory, he proposed that compounds are combinations of two or more different types of atoms. In the fourth and final part of Dalton's atomic theory, he suggested that chemical reactions don't destroy or create atoms. They merely rearrange the atoms. Using our salt as our example, when sodium combines with chlorine to make salt, both the sodium and chlorine atoms still exist. They simply rearrange to form a new compound. To test the properties of the particles, Thomson placed two oppositely charged electric plates around the cathode ray. The cathode ray was deflected away from the negatively charged electric plate and towards the positively charged plate. This indicated that the cathode ray was composed of negatively charged particles. Thomson also placed two magnets on either side of the tube, and observed that this magnetic field also deflected the cathode ray. The results of these experiments helped Thomson determine the mass-to-charge ratio of the cathode ray particles, which led to a fascinating discovery. The mass of each particle was much smaller than that of any known atom. From this evidence, Thomson made the following conclusions. The cathode ray is composed of negatively charged particles. The particles must exist as part of the atom, since the mass of each particle is only 1/2000th the mass of a hydrogen atom. These subatomic particles can be found within atoms of all elements. He called the particle he discovered corpuscles rather than electrons. While controversial at first, Thomson's discoveries were gradually accepted by scientists. Eventually, his cathode ray particles were given a more familiar name, electrons. The discovery of the electron disproved the part of Dalton's atomic theory that assumed atoms were indivisible. In order to account for the existence of the electrons, Thomson knew that atoms had an overall neutral charge. Therefore, he reasoned that there must be a source of positive charge within the atom to counterbalance the negative charge on the electrons. This led Thomson to propose that atoms could be described as negative particles floating within a superdiffuse positive charge. This model is often called the plum pudding model of the atom, due to the fact that its description is very similar to plum pudding, a popular English dessert. His quest actually began when he discovered that some elements give off positively charged particles that can penetrate just about anything. He called these particles alpha particles. We now know they were helium nuclei. Like all good scientists, Rutherford was curious. He wondered how he could use alpha particles to learn about the structure of the atom. In his famous gold foil experiment, Rutherford fired a thin beam of alpha particles at a very thin sheet of pure gold. Based on Thomson's plum pudding model, Rutherford predicted that most of the alpha particles would pass straight through the gold foil. The results of the experiment, however, were striking. While almost all of the alpha particles passed straight through the gold foil, a few alpha particles, about 1 in 20,000, were deflected more than 90 degrees from their path. Based on his experimental results, Rutherford made the following conclusions about the structure of the atom. Since most of the alpha particles passed straight through the gold foil, the atom must be made up of mostly empty space. The positive charge must be localized over a very tiny volume of the atom, which also contains most of the atom's mass, which Rutherford called the nucleus, the dense region consisting of the protons and neutrons at the center of the atom. Rutherford's work became known as the nuclear model. In this model, the electrons move in orbits of fixed size and energy. The energy of an electron depends on the size of the orbit. Radiation can occur only when the electron jumps from one orbit to another. The atom will be completely stable in the state with the smallest orbit, since there is no orbit of lower energy into which the electron can jump. Also with this model, Bohr explained how electrons could jump from one orbit to another only by emitting or absorbing energy in fixed quanta. The orbits are labeled by an integer, the quantum number n. He postulated that the angular momentum of the electron is quantized, it can have only discrete values. He assumed that otherwise electrons obey the laws of classical mechanics by traveling around the nucleus in circular orbits. Because of the quantization, the electron orbits have fixed sizes and energies. He used mathematical equations to describe the possibility of finding an electron in a certain position. This equation describes the system's three-dimensional wave function and is represented by the Greek letter psi. In this equation, the Hamiltonian operator is the set of operations that describes all the interactions that are affecting the state of the system, which can be interpreted as the total energy of the particle. Though the Schrödinger equation can calculate the wave function of a system, it does not specifically reveal what the wave function is. Max Born proposed that we interpret the wave function as a probability amplitude, where the square of the magnitude of the wave function describes the probability of an electron existing in a particular location. The double-slit experiment, the diffraction pattern is not the electron itself, but rather, it is a probability that an electron will arrive at each location. Therefore the Schrödinger equation computes the wave function deterministically, but the information it gives is probabilistic. Unlike the Bohr model, the quantum mechanical model does not define the exact path of an electron, but rather, predicts the odds of the location of the electron. This model can be portrayed as a nucleus surrounded by an electron cloud. Where the cloud is most dense, the probability of finding the electron is greatest, and conversely, the electron is less likely to be in a less dense area of the cloud. Thus, this model introduced the concept of sub-energy levels. The neutron is very similar to the proton except that it is electrically neutral or has no charge. Chadwick found the neutron by hitting a chemical called beryllium with alpha particles.